Why was this really? Lab 4.
Lab 4 is initially I was thinking due the Monday after Thanksgiving. But I want people to do Thanksgiving, so I make it due on Tuesday. So give me one more day. So we will be talking about that today. But I really want you guys to work on transactions because it's really important. So, say about that. But I know people are busy with the final and all that stuff, so it's really tricky. All right, so hello, yeah. Before I start the lecture today, I'd like to do a quick survey among this class. So I have just released Lab 4, which is core optimization, right? Which is, in my opinion, a really interesting product, right? Basically, it tests on your understanding of the core optimization stuff we talk about. And if you look at the way it's really useful for me to show this assignment. So what this one does is, so the outline of the core optimizer is as follows. Basically, it follows exactly the same sequence of discussion we had in our lecture slides. Okay, so we start with an overview of the core optimizer. And this diagram looks maybe complicated, but essentially it is the same high-level diagram I showed in lecture slide, which is you have a plan generator, a statistical data catalog manager, and then a cost estimator that runs between the two. And then you basically iterate through this loop of producing a new plan, estimate the cost, and iterate through this loop until you settle on a fairly good plan at the end of the day. So the first step is to do what we call statistical estimations. And this ties with all the discussion we had about building histograms. And as well as if you do not have histograms, how do you estimate the selectivity for a particular type of query, whether it's join or whether it's selection. We talk about those in our lecture slide, right? And it gives you a very simple formula to estimate the cost of a particular join query, right? For example, if your join is a sequence of join like that, T1 join with T2 join with so on, join with Tn, if you are going to use a left tree plan with the order that's given, the cost is simply this. If you look at it, it's simply scan table T1, scan table T2, the join cost between T1 and T2, plus scan T3, and the join cost of T1 join T2, then join with T3. What that essentially tells you is it's basically a left deep tree plan, right? Basically, right? That's essentially what it does. I scan this, the join cost, scan this, then the join cost of this. Right? Essentially what that formula tells you is essentially you're using a left tree plan to perform your join. And in this assignment, we make it really simple for you to ignore the fact that you may have different join algorithms for the join operator. So we simplify, you optimize it quite a bit. You don't have to worry about that. Rather, you only need to optimize for nested loop join. So we tell you that the join operator is going to be a nested loop join. So you only need to optimize for that. Does that make sense? This dramatically simplifies the job of your optimizer because you don't have to worry about what if I use hash join, what if I use page nested loop join, what if I use block nested loop join. You're always going to use simple nested loop join as your join operator. So, which means to estimate the cost, it becomes really, really simple. And then you talk about how you do selective estimation. There's a lengthy discussion here, but if you have followed the discussion from my lecture, you can safely ignore this. Essentially, we're asking you to build an equal width histogram. Essentially, that's what we're asking you to do. You don't have to worry about equal depths, nor the variance optimization histogram we talk about in class. Those two are more sophisticated than equal width. Equal width is the simplest form of histogram you can ask for, and that's what we are asking you to implement for this project. Okay? And that basically gives you enough background for you to implement access 1 and access S2. Basically building a histogram, scanning table to collect statistics such as mean value, max value, distinct values for a particular attribute. And those are those catalog variables that we need to use in selective estimation, right? So as we show in lecture slide, the curve on the lecture slide. Then we talk about the cardinality estimation for join. This basically follows the similar discussion we provided to you in lecture slides, right? The number of keys from one table multiply the average number of values per distinct value from the other side. That gives you an estimation for the join cardinality, right? We'll talk about that in class. And lastly, the last exercise is about ordering your join, right? So if you have T1 join T2 until Tn, rather than do it this way, maybe you should consider a different order, but still limit yourself to only left tree plan. There's a system test for this where we give you a particular join. If you use the input order as it is, your join will not be able to finish in the time we specified in the system test. So system test will fail. Unless you, of course you can quote-unquote cheat your way out by using a supercomputer like really, really fast. Even for any strong order, maybe you can finish before the specified deadline, right? Time budget. But on typical computer, we did a lot of tests. If you use a typical computer and you don't do any join ordering optimization, you just use the order given from the input, you won't be able to finish in time, specified by that system test. So this join ordering, and what this ordering does is essentially the greedy algorithm we introduce in class. You look at the best one relation plan, best two relation plan, so on and so forth. Then you will end up with a reordering of your join that will, if you reorder your join using this algorithm, still using nested loop join by the way, you will be able to pass that system test. Of course, let me tell you, do not try to mess with the code, because another way to easily pass the system test and cheat your way out is to simply change the test to use hash equal join instead of nested loop join. Then once you change hash equal join, the ordering of the join doesn't matter anymore. I mean, it still matters, but with respect to the system test we have set up, we set out a particular time budget so that if you use nested loop join, using the given order, you won't be able to finish. But if you change to hash equal join, using that order, you will be able to finish. But join ordering optimization for hash equal join still matters, because even if you use hash equal join, if you do this ordering, you will find an even better order that will be even faster than the default ordering. It's just that the default ordering, if you use hash equal join, will still give you a sufficient enough running time to pass that system test. So do not try to change code for that. Make sure you use just the join. Basically, there's one line called initiate join operator. You should new join instead of replacing this with hash. Some of you might have changed this from join to this when you did your lab 3, right? In order to get really good running time for your context. If you have done that, make sure you change back to this. Otherwise, all your optimization code become irrelevant for lab 4. Does that make sense? Yeah? Okay, cool. So that's it. I mean, that's lab 4, and we give you about 2 weeks. Of course, in between there's a Thanksgiving holiday. I don't know how you view this. Maybe it's a few days you can work on your project, right? So I think that is good. But on the other hand, I know you have obligations. You have to visit your family, enjoy your Thanksgiving dinner, all that stuff, right? So that's why initially I set the deadline to be Monday, which is right after the Thanksgiving holiday. I thought about it, I should let you guys enjoy the Thanksgiving day. So I make the due date on Tuesday, give you one more day. To some of you, lab 4, sorry. Now, before I proceed with today's lecture, I want to do a poll to understand what people want to do, okay? We are down the way, right? We are really close to the final. I'll give you 2 options. One is we do only 4 labs, meaning this will be the last lab, and there will be one more homework assignment, by the way. Written assignment 4, that's on transaction, which I will release on Thursday after you turn in your written assignment 3. That's it. On written assignment side, that's about it. On the live assignment 1, I have 2 options for you. Okay. One is we keep 4 labs, and this will be your last lab. So we won't be able to do the transaction lab, which I really, really want you guys to work on, because that's a really important piece of David's kernel. And we keep the distribution of the grid as it is, meaning 50% to project, 10% to homework, and 40% to the final. And final will be basically covering everything from your homework assignments and open book. Okay? So if you feel comfortable doing homework assignment, you should have no trouble in solving the final problem. So that's option 1. Option 2, I will assign lab 5 on transaction, but then it will probably due right around the final week, given the time of it, right? But in exchange, what I will do is I will increase the portion of your project to 60%. Homework only 10%, and final will be reduced to only 30%. Does that make sense? Option 1, option 2. Option 1 is 4 labs, weight distribution, the correct distribution as it is. Option 2, 5 labs, 1 more lab. But I will increase the weight of the product, reduce the weight of the final test. So,
Weight is the last one.
how big? I will show you.
Because mine was on the 12.
Lab 5 is not, if you understand transaction concept that I have discussed and I will be continuing discussing today, lab 5 actually, in my opinion, is easier than lab 2 and 3 and 4. It's probably around the same level of difficulty compared to lab 1, if you ask me. So it's not too bad. On the other hand, are you willing to bet you're going to do really well in the final, right? Because if you go with the option as it is, final is 40%, right? So you're going to bet that, first of all, I will be really nice, give really not so difficult question in the final, and you will do well. On the other hand, if I do give you another lab, that's something you can control, right? Because you work with your teammates, and if you do well, so far, from what I can tell, most of the team got really good grade on your lab assignment. Does that make sense? So you are better off in option 2 if you think your performance on your lab assignment will be better than your performance in the final, right? Suppose you get about 90 or above in your lab, and if you think you can score 90 above in the final, then you should keep option 1. Otherwise, you should consider consider that option 2. Right? That's my rationale of thinking about this. Personally, if you ask me, I prefer to go with option 2 for the fact that I don't want to place too much weight in one final test. If you screw up big time. For that reason, secondly, I feel being able to work on the transaction model is important for you to understand really, because once you do that, you can safely claim after this class, I feel comfortable building Oracle from scratch because you know everything pretty much. Seriously, you are better off than most database engineering outside this classroom already if you finish that file. All right, so that enough said. Let's do a poll. Okay.
What about, if it's option 2, what about a written regression one?
Written assignment is not affected. There will be still one more written assignment, of course. All right, how many go with option 1, which is keep the way it is, do not assign me another lab, and 40% of the time. Okay, all right. She must be really good at this test, I think. And how many go with option 2? Let me repeat, just confirm before you vote, right? Make sure you know who you are working for. Don't just go and say, oh, all Republican, all Democrat, I don't care who the name is. Just go there and Republican, Democrat. You have to know the candidate you vote for, right? Option 2, reduce the final weight to 30%, but then allow me to assign you another lab 5 on transaction. With understanding the due date will be around the final wait time. Okay, how many vote for option 2? All right, option 2 it is. Okay.
I don't know if this is possible. Could you maybe release that lab early?
Yes, I will release. I have the lab ready actually, so I will release. But I don't want to give you guys too much pressure. Right? So what I will do, I will release the lab 5 next week before Thanksgiving, so that you have the option of start working on that once you are done with lab 4.
Because then we can get it done early. And
Yeah, sure. Yeah. I think that's definitely an option. That's definitely reasonable. Okay, so that's it. Right, 30% for final. That way you don't have too much pressure coming to final. And plus, final is open book, similar type of question to your homeworks. So if you can do your homework, or if you haven't done your homework, but you can understand the solution I posted, you should be fine. Of course, if you haven't done your homework, you lose 10% of your price, right? Or you have done your homework, but you really didn't think through it. You just write out whatever you know and didn't really pay much attention to it. Yes, you still got 5% credit over there. You lose about 5%. But as long as you make sure you understand the solution I have posted, can work your way out yourself with reference to that solution, you should be able to do well in the final problem. Okay? All right, so that being said, let's continue with the lecture. Okay. Okay, so we talked about transactions, the overview of transactions, and I talked about, we spent quite some time on isolation levels, and I use this particular example to show you the difference between So we talk about transactions, and I use this particular example to show you the difference between serializable isolation level and repeatable rate isolation level. In particular, for this particular setup, it is not in serializable isolation level. Why? Because at the end of the day, the state you reach is not the same as if you do T1 then T2, nor T2 then T1. That's why it's not serializable. But at the same time, it is a repeatable rate because there are no delay rate, and item read multiple times by one transaction do not change value. Right? Item read multiple times by the same transaction do not change value. So it is repeatable rate. What this simple example illustrates to you is that two things. One is repeatable rate isolation level indeed is a relaxation of serializable isolation. Secondly, repeatable rate isolation level does allow more degree of concurrency concurrent execution in your scheduling of different transactions than, of course, serializable isolation levels. So in practice, as a database administrator, what would you do? Well, you look at a particular application. If it's a really mission-critical application, like banking transaction scenario, you go with serializable isolation level. But if it's like more like student admission and things like that, it's fine if you see some glitch by some user. For example, this user might be puzzled, saying, "Oh, why I'm seeing different output when I execute the same query twice when I'm still in a transaction?" If that's important to you, then you should not go with repeatable wait. But if there is some leeway there, and you expect your user to be able to comprehend that, repeatable wait is the way to go. Because it does allow more degree of concurrent execution of your transactions, which means higher throughput, better performance of your system. Okay. So so I will skip this slide. We spent too much time on that example, so I will just skip that. And one observation is that from that running example is read-only transactions really helps optimize system performance, which is not really that hard to understand, right? Because if you only have read-only operations in a transaction, you are not making any change to the underlying database, then you are not going to interfere with the execution of another transaction. So read-only transactions are really your friend from a database kernel point of view. So the standard is serializable isolation level, and in practice, people design different weaker isolation levels. We talk about repeatable rate, but in practice, if you go to any commercial database engines, the industry standard is to have 4 different isolation levels. We covered the bottom 2 in terms of the level of isolation they can guarantee. Serializable is the strongest. Repeatable rate is the second strongest isolation level. Then there are 2 more isolation levels that typical commercial database engine are able to support. And in most cases, by default, people go with either serializable or repeatable rate. That's why I cover these 2, and the other 2 I leave for yourself to explore. You can, if you're interested, you can just Google online and look through what the other 2 isolation levels are. But typically, people go with either serializable or repeatable rate. Okay. Now, coming back to the general concept of transactions, we said this multiple times. It is a sequence of one or more SQL operations treated as an atomic unit. And it supports both concurrent execution and crash recovery from failures. So in particular, transactions in a database support the following properties. The so-called ACID property. This is extremely important. You need to remember this. So that whenever others ask you what database can do, this is something that you should reply to them, right? It guarantees the important ACID properties. What are the ACID properties? A is atomicity, which we have explained already, right? All or nothing semantics, right? Consistency, which I will discuss in the next slides. Isolation we'll talk about, right? We just explained what isolation is. Basically, what isolation says is that even though there could be multiple concurrent execution of multiple transactions from multiple users, but from each user's point of view, it's like your transaction is running in isolation. You don't have to worry about the fact that there are some other transactions being concurrently executed at the same time alongside with your transaction. Right? So that's the concept of isolation. And durability and atomicity actually go together, right? Because it's all or nothing. Right? Durability means that if a transaction has committed and if your system has crashed, after that, all the changes made by that transaction should be persistent to your database. You may wonder, isn't this automatically true? When transaction has committed, all the changes made by that transaction will be permanently reflected to your database. Well, this is not true by default. I had a simple argument I showed you, I believe, either last lecture or the lecture before last lecture. The reason is you have a buffer manager sitting between your transaction manager and your non-volatile storage media such as disk that store your data. The changes made by a transaction are only reflected to dirty pages in your buffer. And when the transaction has committed, that only means all those changes are reflected to those dirty pages in your buffer. It doesn't necessarily mean those dirty pages have been pushed back to disk by the buffer manager at the time the transaction has committed. Of course, you can simply make an adjustment saying that, okay, fine, what I will do is whenever a transaction has committed, I will ask the buffer manager to push all the dirty pages caused dirty to be caused dirty by this current transaction, and I push all those dirty pages to the disk. That way I can ensure durability. Yes, that's a baseline solution. However, this baseline solution could be really expensive because you are really interfering with how buffer manager works. You are basically saying whenever a transaction commits, you need to push all the dirty pages to the disk, rather than the normal way of buffer manager. The way it works is to only push a dirty page to the disk when it is a candidate for replacement, determined by whatever buffer replacement algorithm the buffer manager decides to use. So later on, we will talk about some different variations of this baseline algorithm that shows much better performance in practice. Okay? So those are the four properties. I think we have a fairly good understanding of atomicity, isolation, and durability. The only thing I need to explain to you is consistency. Right? What does it mean by ensuring consistency in a database engine by the transaction manager? So isolation is achieved by logging, which I will having a detailed discussion right after this lecture slide, so I will skip this part. Durability is achieved by logging. Again, we will come back and revisit this part. Same as atomicity. Okay, so just keep in mind, isolation is realized by using logs. Durability and atomicity are managed by logging, which again, those I will discuss them in details in the follow-up lecture slides. So now let's talk about consistency, right? What does consistency mean, right? So consistency means the following. For every single transaction, you must assume the following, which is all the constraints defined by the functional dependencies, right? I hope you, we didn't discuss functional dependency in this class, okay. All right, so functional dependency is something I covered in my undergrad database class. We didn't cover it here. But what it says is certain constraints that your database must satisfy. For example, I'll give you one example of functional dependency. So suppose I give you a functional dependency called rating determines wage. What does it mean? That means if I have a schema, let's say employee table, I have employee ID, rating, wage, and I like contract ID, like department ID, and things like that, right? So that's my schema. And what I'm going to tell you is I have this constraint which states that rating determines wage. What that tells you is for different employees, if the rating value is the same, let's say rating is 3 here, then their wage, let's say this is the hourly wage they get, right? If your rating is 3, I'm going to pay you $30 per hour. The point of having this constraint is to make sure if the rating value are the same, you pay them the same amount, which is it's a very intuitive constraint, right? You don't want to work for a company where you pay this guy $30 and pay this guy $10 when they receive the same rating. If the rating is different, yes, of course, you can do that slightly different. Let's say a higher rating means a better performance. If rating is 1, yes, you can pay this employee at a lower rate. But if the rating is the same, you better pay them the same. Does that make sense? So in order to capture this constraint, we introduce a concept called functional dependency. Functional dependency. In fact, we have talked about some form of functional dependencies, right? One functional dependency, trivial functional dependency that holds for any schema is what? Is the primary key determines all other attributes. Right? Why? Because if employee ID is 1, I know the rating value must be 3. If you have another record, this must be true. And in fact, this is true because you cannot have another record with the same primary key value. Right? That's why this functional dependency is true automatically. It's automatically true. Right? Another form of constraint Another form of constraint is this primary key, foreign key relationship, right? Primary key, foreign key relationship, right? We talk about this, right? So there are different forms of such constraint in a database. So that means that this actually is a very deep topic. So I just want to give you an overview. The more detailed discussions is found in my undergraduate class. But at least now you understand what this concept is, right? Functional dependency. So what it says is, you can, at the beginning of each transaction, you do assume that all constraints are satisfied by the current database instance. Meaning, if I have a constraint like that, my database cannot have an instance that looks like this. This cannot happen. At the beginning of my transaction, if you have a constraint defined like that, I can safely assume all my instances satisfy this constraint. For example, it must be like this. You follow me? Okay? Now, a basic requirement for any transaction is, at the end of the transaction, when you commit, all constraints are still satisfied. Meaning you do not make any updates to the database that end up in violation to one or more constraints defined against your database. If that's the case, database engine should not allow this transaction to commit. For example, if you say I have a transaction that update employee number 2 rating to $20, when you have this constraint, that transaction should not be allowed to commit. Is that clear? Okay. So a transaction is only allowed to commit when it does not violate any existing constraint defined against your database.
With the theme from last time, if the constraints were satisfied, another tuple can get updated, it would roll back that as well, right? Not just
Say again your question.
So if there was another tuple that was updated and the constraints were satisfied, it would roll back that one as well, not just the one that
Yeah. Now, so that means that that's a basic requirement for any transaction, right? So that means that this consistency property states essentially the following. If you assume each transaction satisfies that requirement, meaning start with a state where all constraints are satisfied, and end up with a state where all constraints are satisfied by each single transaction, if you execute that in true isolation scenario, right? You just execute the transaction by itself. If that's the case, the transaction manager, when interleaving action from different transactions together, must satisfy that at the end of the day, when all the transactions are done, your database is still in a consistent state. Consistent state means that it satisfies all constraints. In other words, yes, you can interleave action from different transactions as much as you want, but make sure at the end of the day, you do not violate any constraints defined against your database. Assuming, of course, each transaction by itself will not result in any violation of the constraint defined against your database. With that assumption, no matter how you interleave these actions, you should make sure you find a schedule where interleaving action from different transactions will not lead to violation of any constraint defined against your database. Okay? So that's what consistency is about. That means that we now understand what is the so-called ASCII properties. And in particular, I think this consistency requirement is actually fairly easy to understand, fairly easy to enforce. Why? Because as long as you have a module sitting within the database kernel that check the constraint at all time, then no matter how you interleave action from different transactions, those constraints will be enforced at all time. So that's easy to enforce. Okay? So what I want to do next is focus on discussing the other properties. How does a database kernel ensure the other properties? And in particular, I will start with isolation. And then I will talk about how to do atomicity and durability in another slide. In your lab, in your lab 5 on transaction, essentially you're going to implement a bare bone structure of transaction manager with the support of isolation. I do not ask you to implement the support for atomicity and durability, meaning a part of it, but not the full part of it. You will understand what I mean by that when we touch on those topics. So let's go to this particular part. How does the database kernel ensure isolation? Okay. For that, we will use this module called concurrency control. So I explained to you what a semaphore is about, right? At the very beginning of the discussion on transactions, we talked about semaphore. And semaphore was invented a long time ago for control trains coming in and out of a train station, right? When you have many tracks, they come together. How do you avoid collisions from different trains on different tracks? Well, you use semaphore, right? So this is semaphore. These guys are called semaphore. Yeah. In the context of train station, right? They do not call them traffic light, right? Of course, you can still understand them as traffic light, but essentially that's semaphore. Yeah. Now, semaphore is used to do what we call concurrent execution of different transactions, and concurrent execution of different transactions really is to satisfy the given isolation level requirement. If you're in serializable isolation level, I should do this. If you're in repeatable rate isolation level, I should do that. So in our discussion, we will focus on serializable isolation level. So suppose your database engine is set to serializable isolation level. How does the database kernel actually support that? Okay, that's what we will be discussing next. So the technical workflow is that users submit transactions, and because of the isolation requirement, a particular user can think of each transaction as executing by itself, without worrying about the fact that, oh, many other users may be accessing my database at the same time. This isolation level concept is really useful for users to reason about his or her transaction without worrying about other actions by other users, right? Because without this requirement, without this property, it's really hard for anyone to actually use your database, right? Because I'm trying to, for example, move student record from apply to archive. What if somebody tries to update student record in the meantime? How should I rewrite my code? Without isolation, you need to worry about all these issues. But with isolation, you don't have to worry about those issues. You follow me? Right? That's the point of isolation, right? But the challenge is, how is it actually done inside a database engine? So this actually is a review of atomicity and acid properties. I will skip all those. I will go directly to this example where I have used this example already, this balance transfer between two accounts, right? So I have two transactions. Transaction 1 basically says I'm going to move balance between two of my accounts. I'm going to move $100 from account A to account B. And suppose this happened around the same time when bank decides to issue some interest to all the accounts within that bank. In particular, it decides to give 10% interest rate to all the accounts. So what it does is to do this too. Of course, there could be more accounts than just A and B, right? But for illustration purposes, I will assume there are only two accounts that's affected by this action. So we only do interest rates for those two accounts. serializable isolation level says you must ensure the execution of these two transactions, leaves the database in a state that's equivalent to either or this. Right? That's what we mean by serializable isolation. Right? So you can interleave action from different transactions, but at the end of the day, it must be equivalent to either this or that. And there are different ways you can interleave them, as I demonstrated to you last time in whiteboard. So I'm going to repeat this example right here. So I can do that, or I can do this or this. Do this, right? So the first one actually is okay. If you check it, it's the same effect as what? As if you do T1 then T2. Right? The first schedule of interleaving action from those two transactions leads to a state where it is exactly equivalent to this. So that first one is okay. But what about this approach? This approach is not okay. It favors the account holder because basically you get interest twice on that $100. So from a bank point of view, you do not want to see this. Right? Of course, there is another scheduling option I didn't show here, which is you swap these two and swap these two. That way, the bank avoids giving out any interest at all to the $100. So bank will favor that, but account holder will be disappointed with our approach, right? So either of these two is not okay. The reason is there, if you check it, it's not equivalent to this, nor is it equivalent to this. That's why it is not in what we call serializable isolation levels, right? Now that being understood, the challenge now is to design a mechanism that runs within the data kernel that can automatically figure out which is okay, which is not okay, right? That's the challenge, right? So the way we're going to do this is to use a really simple abstract view of transaction executions inside a database kernel. This abstraction basically says the following. From a transaction manager point of view, I don't really care what you are doing within a transaction. What's the semantic application or semantic implication of your transaction? For example, I don't really want to care you are moving $100 from account A to account B, or you are giving out interest. From transaction manager's point of view, all you are doing is you read the value of some object. Then you go around and do something about that. And you come back, ask me to write some value back to the object. Whether it's moving $100 away from the account or giving 10% interest, irrelevant. From my point of view, all you are doing is you read the value of A, you do something about it that I don't care. That's you do in buffer manager, and it's a CPU instruction, execute it against a page in my buffer, and then you come back, ask me to write the value of A. Right? Whether you plus $100 or plus $1 million, irrelevant. Now, coming here, what you ask me to do is read the value of A again. You do something about it. Here you give interest out. Well, it's actually 6% interest. For some reason I lowered the interest rate. Okay. So you write the value back. You read the value B, you write the value of B back. Then finally you read value B again and write value B back. Of course, by these are actions from different transactions interleaved together. So this is the abstraction we're going to use in our discussion, right? So we're going to ignore the semantic implication of those actions. Rather, we focus on only the read and write from those actions. And that helps us greatly simplify the discussion and focus on the important challenges we need to address. Okay? Now, to understand why this particular schedule, is not okay, we cannot ignore this. We just focus on this. Just focus on this. So, what is not okay with that schedule? For that, to initiate that discussion, let me first introduce a couple of concepts. The first concept is what we call serial schedule. These are serial schedules, meaning there are no interleaving of action from any transaction. You execute them in true isolation, one by one. Then that's a serial schedule. Okay, this is very simple to understand. And next, I will introduce a concept called equivalent schedules. Equivalent schedule says two schedules are equivalent if at the end of the day they leave database in the same state. Then they're equivalent. For example, this schedule is equivalent schedule to this schedule. Because at the end of the day they leave database in the same state. So far so good? Okay? Fairly simple concept. But this one is not equivalent to any of this. Okay? However, this one is equivalent to if you were to swap these two actions. Then those are equivalent schedules. So if you swap these two actions, then that leads to an equivalent schedule. So far so good? With these two concepts in hand, we can introduce the final concept that's really important to our discussion, which is what we call serializable schedule. Serializable schedule is a schedule where it is an equivalent schedule to some serial schedules. That's the definition of serializable schedule. That means that this, the first one on top, is a serializable schedule. Why? It is because it is an equivalent schedule to one of your serial schedules. So it's serializable schedule. This one at the bottom of this one, these two, it is not a serializable schedule because it is not equivalent to any one of your serial schedules. You only have two serial schedules here, and it's not equivalent to any one of these. So it is not a serializable schedule. Okay? With this concept in hand, now we can formalize what's the requirement for serializable isolation level. What's the requirement for serializable isolation level? Well, the requirement for serializable isolation level is very simple, which is to only allow and permit what? Serializable schedule. To only allow and permit serializable schedule. If you somehow manage to do that, you are in serializable isolation level, guaranteed. Because that's basically the definition, right? Because if you only allow serializable schedule, then no matter what you do, you end up to be equivalent to a serial schedule, which is precisely the definition of serializable isolation level. So the problem of building serializable isolation level is reduced to finding schedules that are serializable schedules. These two now are equivalent. Okay, these two problems now are equivalent, right? So now we're going to focus on how we design serializable schedule. And for that purpose, we're going to introduce what we call anomalies between actions. In particular, we're going to introduce three types of anomalies. The first anomaly is what we call read and write conflict, or write and read conflict. Let's see, maybe I made a mistake. Reading uncommitted data. Yeah, so WR conflicts. What this says is a transaction in your schedule, one transaction attempts to read uncommitted data by another transaction. So for example, in this particular schedule, this is a WR conflict on A. Why? Because your transaction 2 is trying to read the value A written by transaction 1 which is not committed yet. You may wonder, what's the problem with that? What's the problem of reading uncommitted data by another transaction? Can someone try to think about why we want to prevent this from happening? Yeah.
Like, I mean, like at the end of the T1, we have a board. What happens if they abort?
Yeah.
Then it's fine, but if not, then.
Yep, that's right. So this goes back, I think I've talked about this, cascading abort, meaning the rollback or abort of one transaction leads to the rollback and abort of other transactions. If you allow WR conflict to exist in your schedule, if you allow WR conflict to exist in your schedule, meaning you allow one transaction to read uncommitted data by another transaction, you introduce a potential risk of cascading abort. For example, in this case, instead of, so proceed, okay, and T2 has committed. That's important. T2 actually has committed right here. And T1 come back and abort. And then you have to tell T2 to come back and abort, even though T2 has already committed. This doesn't make sense. You will puzzle the users, right? It's like somebody go to vote and get the speaker unvoted, and then receive a call, oh, because the other person didn't vote properly, you have to come back and re-vote. That's not okay. People are not going to like a system like that, right? Either you say, okay, you do not allow T2 to commit. You do not allow T2 to commit. And that's one possible solution, by the way. If you want to allow WR conflict, which is if you have a WR conflict, meaning one transaction reads uncommitted data by another transaction, one way to fix that is the second transaction cannot commit until the first one has committed. That way you ensure there will be no cascading abort. However, if you do that, that goes against the concept of what? Isolation. That goes against the concept of isolation, right? Because isolation, all isolation says is transactions should not worry about what other transactions are doing. Do you follow me? So that goes against the very principle of isolation. So we should not allow WR conflicts. Okay, so that's one type of anomaly, very easy to understand. Okay. The second one is what we call RW conflict. RW conflict. By the way, when I say WR or RW, obviously it refers to the same object, right? If you write object B and the other transaction read object A, that's okay. There's no conflict whatsoever there. It must be on the same object. Secondly, these WR actions are from different transactions. If it's from the same transaction, obviously it's okay. I read something, I read something, that's okay. Because you are still one transaction, there's no cascading abort to begin with. Okay? What's wrong with RW conflict? Meaning, like this. This is the RW conflict. Not RW conflict. RW conflict. Sorry, RW conflict. You read the value A, somebody then read the value A. So one transaction read an object A, then another transaction come back and read the object, read the value of A for the object. What's the potential challenge for that? Well, keep in mind we are in serializable isolation level, right? We are not in repeatable rate isolation level. In serializable, we are in serializable isolation level, which is a stronger requirement than repeatable rate isolation level. Right, by the way, if repeatable rate isolation level already doesn't allow you to see the same item read multiple times to change value, obviously, serializable isolation level will not allow that to happen as well, because it is a stronger isolation level than repeatable rate. For that argument, we cannot allow RW conflict, because if you do allow RW conflict, it's potential risk that the same object you have read already might have changed values because the read operation from another transaction. So, for example, so these two bits on the same object A might have changed values. You follow me? That's why we cannot allow RW conflict. We cannot allow RW conflict. to ensure items read multiple times are not going to change value.
So, looking at that, is there any reason why, like in our optimizer or maybe somewhere else, we could see, we look at T1 and say, okay, you're reading from A, and then you're going to just read from A again. That's a duplicate thing, there's no sense of doing that, just removing it.
That's a good question. So the question is, why you are reading the same object twice? Why? Why do you want to do that? Why somebody wants to read the same object twice, right? Why don't you just remove the read of the second object? Well, this goes back to, this is actually not a problem pertaining to just transaction, right? So in your coding of any program, the fundamental question you are asking is, should we allow a programmer or a program to be able to read the same object twice? Or should we just simply forbid that? Prevent that from happening altogether. If you think about it, obviously we cannot prevent this from happening, right? It's like recursion. You have to be able to read the same object twice if you want to support recursion. And there are many, many reasons where you have to allow this. So you cannot simply say, I do not allow you to read the same object twice.
So, but in that case,
In one transaction or in programming context in one thread.
so in that case though, you might potentially be changing that variable. But in this case, like we're reading RA, and then like the next thing we're doing is reading RA. So it'd be like setting a variable to 7, and then the next line is set that variable to 7.
Well, I'm using this is a very extremely simplified example. Right? There could be other things going on between, but that's just irrelevant to our discussion, so we just remove that. But you can imagine there are maybe other actions here, but just irrelevant to this discussion, they're just removed. Okay? And also keep in mind, the other thing I want to keep in mind, I want to remind you is, these things happen in an online fashion. You cannot see the future. You do not know at this point that the same transaction will come back and request the value of A again. You cannot predict what the future looks like. It's an active online transaction. That's why transaction in database is called OLTP. TP is easy to understand, transaction processing. What's OL? Online transaction. So it's online, it's not offline. So whatever we do, we have to figure out a way to do this in an online fashion without knowing the future. Right? That makes the problem much more challenging than if you know the future. So we understand why we cannot allow WR conflict or RW conflict. Right? Finally, the last anomaly is a little bit less obvious to understand compared to the other two, which is WW conflict. So look at this particular example. I have one transaction read the value of A, and then before that transaction come back and read the value of B, the other transaction comes in and read the value of A and B and commit. And then the first transaction comes and read the value of B and commit. You might wonder what's wrong with this. It looks okay, right? What's wrong with, there is a WW conflict, meaning this pair or this pair, right? Both transactions are reading the same object. The potential challenge of allowing WW conflict is that it's no longer a serializable schedule. It cannot be equivalent to one of the two serial schedules. What are the two serial schedules here? T1, then T2, or T2, then T1. In the first case, what's the final value of A and B? Well, the final value of A and B are determined by T2. What about the second case? What's the final value of A and B? It's determined by T1. But if you allow WW conflict to exist, what happens? Well, it's potential that the value of A is determined by T2, the value of B is determined by T1. So by definition, it is not a serializable schedule. It's really subtle, but if you think through, you see why WW conflict is not okay. For serializable isolation level, for serializable isolation. And this schedule, if you think about it, is actually totally okay for repeatable rate isolation. There are no dirty rate. Action right number time to launch value. So this schedule is allowed in repeatable rate isolation, but it's not okay in serializable isolation. Do you follow the argument? Why is okay in repeatable rate? First of all, there are no dirty rate. There are no rate at all to begin with, so it cannot be dirty rate. Secondly, action right multiple time cannot change value. No action has been right multiple time by the same transaction. So of course it's okay in repeatable rate, but it's not okay in serializable level because it's not equivalent to this or that. Okay? So using these two simple slides, now we understand how to ensure serializable schedule, right? To get serializable schedule, essentially what we want to have is no RW conflict, no WR conflict, and no WW conflict. As long as these three are checked, good news, you are in serializable isolation level. Or you are going to have serializable schedule, hence you will be in serializable isolation level. So we reduce the problem to this, okay? To this. The next question is, how do we ensure there are no such conflicts in an online fashion, right? That's critical, in an online fashion, in a truly online fashion. Offline, this problem actually can be easily solved. If I give you all the action from all the transactions, you can come up with a schedule without any of these conflicts. Fairly easy, fairly easy, fairly easy. Okay. What about doing this in an online fashion? Okay. For that, we introduce this famous protocol called two-phase locking protocol. There are two variations. So let me introduce each one of them. There's a subtle difference of the two. You know, two-phase locking protocol by itself is not hard to understand. What's difficult to understand is the difference between the two variations it offers. Okay? So let me try to explain this to the best way I can to you. Okay? So first of all, we start with the basic form of two-phase locking, which is called strict two-phase locking protocol, strict TPR. Strict TPR. And this is what you will be implementing in your lab file. You will implement strict TPR in your lab file. Okay? So what's strict TPR? First of all, I introduced the concept of locks. We introduced the concept called locks. And locks are introduced over objects in your database. Object can be a tuple, a record, a table, or even the whole database. Right? For now, let's simplify our description. Let's say object is simply just a record in your database. Okay? Now let's think about record as just a single record. Right. We got assuming to simplify the discussion, A and B are simply records in our database. Okay? That's one thing. And logs, we introduce two types of logs. One is called exclusive log. The other is called shared log. And this is known as X, this is known as S. And I'm going to introduce this compatible table, log compatible table. It says on any given object A, I'm going to introduce what we call compatible table. What it says is exclusive log is not compatible with exclusive log. Exclusive log on A is not compatible with a shared log. Vice versa. But a shared log on A is compatible with a shared log on A. What that means is if some transaction is holding a share lock on object A, another transaction requesting a share lock on A can proceed. So multiple transactions can hold a share lock on A at the same time. However, if there is one transaction holding an exclusive lock on object A, then no other transaction can acquire any lock, exclusive or share, on that object A. That's what it means. Okay, so that's first of all the concept of lock, and two types of locks. Straight two-phase locking protocol is using. That being said, straight two-phase locking is very simple. It says the following: each transaction must obtain a share lock on an object before reading. So if you attempt to read A, what do you do? Before that, you must do this. If you try to write the object A, before that, what you must do? You must obtain an exclusive lock on A. You follow my argument? What if you try to obtain an exclusive lock on A? So this is T1, let's say. And T2 has, before you obtain an exclusive lock on A and write the value of A. Now you T1 try to obtain the exclusive lock on A. What happened to this? Well, it will be blocked. So you cannot proceed to write the value of A. It will be blocked because of this. You follow me? What about this? If T2 has already a shared lock on A and read the value of A, well, that's okay. You can proceed. But in that scenario, this will be blocked. Because this exclusive lock is not okay with the shared lock over there, so this whole thing will be blocked right here. Okay, so that's the idea. So this first requirement is to introduce to you how to acquire locks, right? You must have a way to release locks. You cannot just acquire locks, right? If you keep acquiring locks, nobody can proceed. So there must be a way for transactions to release locks, right? So that's when it differs. There are two variations of two-phase locking. That's when it differs. In the straight two-phase locking, in the base version of this protocol, it says all locks held by a transaction are released when the transaction completes, meaning when transaction commits. Either commits or aborts, by the way. When transaction commits or aborts, you release all the locks you have acquired so far. That's straight two-phase locking. The non-straight two-phase locking says the following: the way you acquire lock is the same, but the way you release locks is slightly different. What it says is you actually can release locks anytime. You don't have to wait until you commit or abort to release locks. However, this is important. However, you better know what you're doing. Meaning, once you start releasing locks, you can no longer acquire any new locks after releasing the first lock. You cannot acquire any new locks after releasing the first lock. You may wonder, hold on a minute, what's really the difference between the two? What's really the difference between the two? Well, the point is, the first version says you release lock all at the same time. You may have hundreds of locks. You release all of them at the same time. The second version says, you know what? As long as you have acquired all the locks you need and you're done with some of your locks, you can release those first while holding on to some other locks. So I may still hold a shared lock on B, but I'm done writing the value of A, so I can release exclusive lock A right away, rather than wait until you commit. There's a huge difference, by the way. Let me illustrate that using a simple example. Okay? There's a huge difference of the two. So let's say I want to do the following. I do share lock on A, and then I will read the value A, and I can proceed. Now this guy tried to obtain an exclusive log A and to write the value A, potentially to write the value A, but this will be obviously blocked because of this. You cannot proceed. You cannot proceed. Now this guy said, I'm gonna, once I know the value A, maybe I use the value A to compute the value B to update, right? So I will do something, so I do something here. So that's CPU cycles. Then I come back, say I will write, obtain the exclusive of B, and try to write the value of A. You know, but, and then I will do something else, I will, and suppose it's a sequence of operation, I update these guys one by one. But note that since you are still holding the shared lock on A, while you are doing all of this guy cannot proceed. You want me? Yes? So straight two-phase locking says, when I commit, this is when I release what? This is when I release all the locks. So only after I commit, I will be able to, this transaction will be able to acquire that exclusive lock and proceed. You follow me? This is strict two-phase lock. So far so good. What about non-strict two-phase lock? Well, this is still okay if you are non-strict two-phase lock, because once you release lock, you do not acquire any new lock, so it's okay. However, I can do better than this. What I'm gonna do is, right before I do that, right before I acquire the lock on, so what I will do is, instead of doing this, what I will do is do this. Before I do the write of each object, I will acquire all the locks I need. Maybe writing to this object takes a long time. It's a big object, takes some time. So I will acquire all the locks before I start writing to any one of them. For non-strict two-phase locking, allow you to what? Because at this point, you no longer need to acquire any new locks. And then this guy can immediately see right here, rather than wait until then. And then you can proceed with. And at that time, you can release the other exclusive lock. Another alternative is to release you release the lock immediately after you're done with it. But one thing to note is that you cannot release, you cannot do this though. You cannot say release here and to allow WA to proceed right here. This is not okay, even in strict two-phase lock, even in non-strict two-phase lock. Why? Because you are still acquiring new locks after you have released locks, which is not okay. So that's the subtle difference between the two versions. Do you understand?
So, question.
Yeah.
So does that mean that you can only release it once, or
you can release multiple locks, but the point is, after the release of the very first lock, you can no longer acquire any new locks. There are no restriction on how many locks you can release before you commit. But once you start releasing locks, even just one, you no longer can allow to acquire any new locks. Whereas in strict two-phase locking, it's much simpler. You can acquire locks as much as you want, as long as it's compatible by other locks, held by other transactions. But you only release lock when you're ready to commit or abort. You don't release locks before that at all. So what's the difference? Now here are the important claims. Strict two-phase locking allows only serializable schedules. and it does not introduce cascading upward. So it only allows serializable schedules and does not allow cascading upward. What about non-straight two-phase locking? Non-straight two-phase locking says it also only allows serializable schedules. But at the same time, it may introduce cascading upward. So that's the subtle difference between the two. So I will skip this because I talked about this already in the class. I will use this figure to demonstrate to you the difference between straight two-phase locking and non-straight two-phase locking. Okay? So straight two-phase locking says, by the way, y-axis is number of locks you have obtained, x-axis is time of your execution. In both cases, there is a growing phase, meaning you are acquiring locks. So that's why the number of locks keep going up. And then you do some computation. Well, you can do computation even while you are still acquiring locks. So computation can still be carried out here. But for straight two-phase locking, the number of locks goes to 0 in display only at the time either commit or output. So this curve looks like this. What about non-straight two-phase locking? There's a phase you acquire more and more locks. You do computation. This is the time when you first start releasing lock. This is the time when you release the very first lock. And once you do that, the curve gonna go down because the number of locks gonna reduce. The point is, once you go down, can you go up? You cannot go up. You have to go down all the way. It could be a general case of that is maybe looks like this. You compute, you reduce, stable, come down. But you can never do something like that. Very locks, come down, go back up. That's not. But for straight two-phase locking, it's always going to be like that. In both cases, you cannot, in the growing phase, you cannot come down and grow again. These are not okay for both cases. Okay? And the bottom line is both protocols allow serializable schedules and but non-straight two-phase locking may permit cascading abort. So, according to the transaction, so how do you abort a transaction? So, okay, let me talk about this and I will stop. Okay, if transaction Ti is aborted, all its action has to be undone. So how do you undo a transaction? Well, you use something called log. We will talk about that in the next lecture slides. So log is something that you keep around on permanent storage media that remember what has been done by a particular transaction. Not only that, if Tj, another transaction, reads an object last written by Ti, then Tj must be aborted as well. Essentially, you are reading an uncommitted object. That's why Tj must be aborted. So with this being said, Tj, the abortion of Tj may in return lead to rollback or abort of another transaction. That particular phenomenon is called cascading abort. Straight two-phase locking does not allow cascading abort. Non-straight two-phase locking may allow cascading abort, but both only allow serializable schedules. Okay? So there's a short discussion of log. I will skip. Now, before I proceed, I will stop right here. Yeah, question.
Like T1, if it gets blocked, does it just wait until it's unblocked, or?
Very good question. So, if T1 is blocked, should T1 just wait or do something else? In the case T1 waits, is the wait indefinitely long or something? And this goes to the topic of.
Or would
what we call deadlock. I will show you really quick. So for example, it's possible T1 is waiting for a log held by T2, T2 is waiting for a log held by T3, and T4 is waiting for a log held by T2. So far this is okay, because as long as T3 releases the logs, T2 can proceed, and eventually T2 will release all the logs, and T1, T4 can proceed. So this is okay. But imagine T3 says, well, I realize I need to prepare logs that's held by T1 on different objects, right? T1 is waiting on A, T2 is waiting for B, and T3 is waiting for D that's held by T1. Now what happens? Nobody can proceed. Nobody can proceed. And this is called deadlock. And that goes back to your question essentially. Unfortunately, I don't have time today. I will resume the discussion on Thursday. Before I let you go, I mentioned to you already, tomorrow I have to go for a meeting at DC. I come back on Friday. I could just cancel the third lecture on Thursday, but I feel like we just don't have the luxury of canceling lecture at this point. So I will ask my PhD students to come and do the lecture on Thursday. Robert and Joya will be here. And they know this stuff really well. They actually write transaction engines. So they know this stuff really well, so they should be able to do a very good job on Thursday. Okay, see you on Thursday. Homework is due on Thursday, okay?
So we bring it to class and give it.
Give to the PhD students, my PhD students, then they will pass to me. Even though